if you're talking about regular, ordinary calculus 1 derivatives, it's really easy to manipulate those derivatives in terms of like multiplying and dividing and canceling, that kind of thing. And so let's first look at this example. And I'll point out where I'm manipulating the derivatives and what I mean by it being easy to manipulate ordinary derivatives. And so this example is what's called a differential equation. And it's a differential equation because in this one equation, I have the variable y and I have its derivative, the derivative of y with respect to t. And so what's implied here whenever I write this differential equation, it's implied that y is a function of t. Or y depends on an independent variable named t, right? So maybe you've seen this before, maybe you haven't. That's fine. I'll show you how to solve this whole thing. The first thing I'm going to do is divide both sides by y times 1 minus y. Okay? So on the left side, I'll have 1 over y times 1 minus y times dy dt. And then on the right side, I just have 1. Because I want to get rid of the derivative dy dt, I'm going to take the antiderivative of both sides with respect to t. And since the left side is equal to the right side, then the antiderivative of the left side should equal the antiderivative of the right side for some constant, right? What I mean whenever I say that ordinary derivatives, or ordinary differentials you might say, are really easy to manipulate is because in this step where I see dy dt dt, what I can do with ordinary derivatives is I can just say that that dt in the denominator cancels with that dt in the numerator, and now this is the same thing as taking the antiderivative with respect to y, okay? That's something you can do with ordinary derivatives that you can't do with partial derivatives. And now, hearkening back to our calculus 2 days, that antiderivative on the left side can be solved using partial fraction decomposition. And partial fraction decomposition says if I've got 1 over y times 1 minus y, this is equal to some constant divided by y plus some constant divided by 1 minus y. And if I want to find what that is, what those constants are, I can multiply both sides by the denominator on the left side, and I get 1 equals a times 1 minus y plus b times y. And that means 0 is equal to negative ay plus by, and 1 is equal to a. So then b is equal to 1, and we found that 1 over y times 1 minus y is equal to 1 over y plus 1 over 1 minus y. And so we call that decomposing a rational function. Since my integrand was a rational function, we just decomposed it into 1 over y plus 1 over 1 minus y. Okay, on the right side, the antiderivative of 1 with respect to t would be t plus some constant that we don't really know yet. Don't really know about that constant. Go ahead and get rid of my work there. Okay, and then taking this antiderivative is not so bad. This is just going to be the natural log of y plus the natural log of 1 minus y equals t plus c. A property of logarithms, though, would tell me that this is the natural log of y times 1 minus y, because I'm adding two logarithms, right? And
should only be negative log of 1 minus y.
Oh, yeah. Sorry. Good point. Yeah, so you got the negative y on the inside, and so that should be minus. And then you're right. So the minus should be y over 1 minus y inside the logarithm. Thank you. I was going to be confused here in a second if you didn't correct me. So then y over 1 minus y is going to be equal to e to the power t plus c. C is just that constant. And I haven't really specified what that constant is yet. So what I could do is use a little property of exponents that says if I'm adding in the exponent, that's the same thing as multiplying. But again, since that c is allowed to be any number, negative or 0 or positive, then e to the power c is again just an unspecified positive number. So really, this is equal to some positive number. But I can just write it like that, remembering that c is an arbitrary constant. You can choose whatever you want for c. Okay. Now, as I solve for y, let's see what happens. This is going to be c e to the t minus y c e to the t. And so I'll add that to both sides and then factor out the y and then divide, and I'll get y equals c e to the t divided by 1 plus c e to the t. If I did that right. Double check my work. So we add that, factor out the y, divide. I think that's right. Okay. Yeah, great question. So in this step, what we did is we took the exponent base e of both sides, the left side and the right side. On the left side, it cancels the logarithm. On the right side, we would get e to the power t plus c. E to the power t plus c is the same thing as e to the power c times e to the power t. But here's the line of reasoning, is that c is an arbitrary constant that we picked up by taking the antiderivative. That can be whatever you want. That could be negative 500, it could be positive 42, we just don't care, right? And if I don't really care about that constant, then that means e to the power c could take on any positive value, right? As long as c is a real number, then e to the power c is any possible positive real number. And so what I did is I just replaced the e to the power c with just a c, and then I specified that that arbitrary constant c can be anything as long as it's a positive real number. Okay. So anyways, this is what you would call the solution to the differential equation. That function y as a function of t, that's the solution we found. That's the function or the family of functions that fits and works with this differential equation I started out with. Okay, that's not the purpose of today, but the purpose of today is just to point out that whenever we have a ordinary derivative, like we talk about in Calculus 1, or Calculus 2 for that matter, you can manipulate them as if it was just like a normal variable, right? Like when I have dt in the numerator and dt in the denominator, we could just cancel those out. And that was a really easy way to solve this problem. Okay. Another place where we do this is when we do u substitutions. So if I have the antiderivative of 2x e to the power x squared dx, what's my u substitution that I'm going to try? X squared, and then du is equal to 2x dx. And what we're really doing here is actually saying that the derivative of u with respect to x is 2x, the way that I've defined u. Okay? And then what I'm saying is that if I were to write this, 2x e to the power x squared du dx dx, then I could cancel out these dx's, but oops. Then what I have to contend with is the idea that, again, it's easy to just manipulate these differentials, right? What I mean by manipulate the differential is like if I've got it in the denominator and I want to cancel it and get it out of the denominator, I can just multiply both sides by dx. I can pretend that it's just a variable, and everything works out really smoothly. I'm really making a big point of this because we can't do the same thing with partial derivatives. And I'm going to show you that here in a second, but a couple more examples here. If I have the derivative with respect to x of sine of x squared, I would first take the derivative of the outside function, and then I would take the derivative of the inside function, which is 2x, right? So practically speaking, if we say that y is a function of x and x is a function of t, then taking the derivative of y with respect to t would be like taking dy dx times dx dt. Okay? That's how you would state the chain rule in terms of, what do you call this? It's not the Lagrange notation, it's the Leibniz notation. This is like the Leibniz notation statement of the chain rule. And again, the reason that it's really intuitive and everyone can see at a glance why the chain rule works is because these differentials, these ordinary differentials, are really easy to manipulate. I see one in the numerator and I see one in the denominator, and you can just cancel those out, and then look, you have dy dt. Okay? When we were talking about the length of a curve, where y is a function of x in the xy plane, if I wanted to calculate the length of the curve, we were talking about taking a little chunk in the x direction, dx, and a little chunk in the y direction, dy, and that gave me a little length of curve, which we called ds. And then we used the Pythagorean theorem. We said the x direction and the y direction are perpendicular to each other, and so the Pythagorean theorem says that ds is going to be the square root of dx squared plus dy squared. And that doesn't tell us how to compute the length of the curve. I know for the length of the curve, I'm trying to add up all the little ds's, so this is the integral of ds. But that would just tell me that I take the integral of square root of dx squared plus dy squared. And again, I don't really know how to calculate that. The way that we made this into something worth calculating is I said, let's also multiply times dx over dx. And I can do that because it's kind of like a variable. Dx over dx should just be 1. And then if I move the 1 over dx inside the radical, inside the square root, I have to square it. And so this is dx squared over dx squared plus dy over dx all squared. And I get the dx at the end. And then I can cancel these out because they're numerator and denominator. And then our formula for the arc length of a curve that we talked about in Calculus 2 was the square root of 1 plus dy dx squared dx, right? Again, the point of this is to point out how you can manipulate ordinary differentials really easily. You could, just multiply by dx over dx, and then you could move the reciprocal inside the radical, and then you could cancel these out because it was numerator and denominator the same. And so you can treat it like a variable, and that's really, really nice. Okay, the point of all this is to say that the partial derivatives are not easily manipulated the way that we can manipulate ordinary derivatives. And here's an example. If we look at the ideal gas law from chemistry, the PV equals nRT, and suppose that we wanted to calculate what is the partial derivative of t with respect to p times the partial derivative of p with respect to v times the partial derivative of v with respect to t. We want to know what that is. If I could easily manipulate partial derivatives, the way that we could always easily manipulate ordinary derivatives, then I would say, look, I've got a partial of pressure in the numerator, and I've got a partial of pressure in the denominator, right? Cancel those out. I've got a partial of volume in the numerator and a partial of volume in the denominator, so cancel those out. And then I've got a partial of temperature in the numerator and a partial of temperature in the denominator, so that should just be 1, right? That's what I would say if I could just do these algebraic manipulations. If I could treat the partial differentials like they were variables, we could do that. Okay? So let's actually work out the whole problem the long, boring, tedious way, and let's see what we get. So the partial of t with respect to p in this equation, I would have to say that t is equal to pv over nr. So taking the partial derivative of t with respect to p would be v over nr. Okay? Now, what if I want to take the partial of p with respect to v? Then I could write p equals nRT divided by v. What's the partial derivative with respect to v? Mm-hmm. Yeah, I pick up a negative, because that's v to the negative 1 power. nRT over v squared. Okay. Then, what's the partial of v with respect to t? I could write v equals nr over p times t. And so the partial with respect to t would be nr over p. Okay. Now let's cancel these variables out, because they actually are variables and I'm allowed to cancel things. I've got this r in the denominator. I've got an r in the numerator. I can cancel. An n in the denominator, an n in the numerator. A v in the numerator, a v in the denominator. And then I can't cancel anything out yet, so I can, for the moment, just write negative t in r over vp, which is a little jumbled up. Let me write negative nRT over PV. And again, what my ideal gas law was saying before is that PV is equal to nRT. If I divide both sides of this equation by PV, I would get 1 is equal to nRT over PV. So that means the answer to that multiplication of that sequence of partial derivatives is actually not 1, but negative 1. So that means we can't just willy-nilly manipulate partial derivatives we could with the same way we could with ordinary derivatives. This is a firm counterexample to that. And this is honestly the reason why I was having so much trouble figuring this out like a month ago whenever we were talking about 13.5 for the first time, is because I legitimately thought that was possible. I walked into class thinking I was prepared for a lecture because I thought you could do stuff like that. You could just cancel it and treat it like variables. And so this was a surprise to me the first time I saw it. So you got to be a little bit more careful whenever we do implicit differentiation with partial derivatives. We've got to be aware of that. We can't just cancel stuff out. Okay, so now suppose we have an equation and the equation is going to be in terms of three variables, x, y, and z. And we could always rearrange any equation involving those three variables to look like this. We could always have some function of x, y, and z equal to 0, right? If your equation looks something like different, like a function of x and y equals some function of z, you could just subtract the whole right part and then you could make it look like this, right? So we can always rearrange to make it look like this does. Well, we could take the total differential of f, the total differential of the left-hand side of the equation, and this should be the partial of f with respect to x dx plus the partial of f with respect to y dy plus the partial of f with respect to z dz. Okay. Now what if I want to find the partial derivative of z with respect to x? If that were the case, my first step is going to be to start with this total differential of f and then take the dx in the denominator. And since this is an ordinary differential, a dx, I can kind of treat it like a variable, and I just have to now put a little dx in the denominator of every term on the right-hand side. So I get partial of f with respect to y, dy dx, and then partial with respect to partial of f with respect to z times dz dx. Okay? So this dx dx, again, easy to manipulate because it's an ordinary differential. That's just going to be a 1. And also, we need to remember that in my equation, we said that capital F, while it was a function of x, y, and z, it's always going to be equal to 0, and that's how we're defining the relation between variables x, y, and z. So this is true for all values x. So that would mean whenever I see the partial of f, sorry, not the partial, let me take that back. Whenever I see the derivative of f with respect to x, as long as x stays in this relation, stays locked in here, that has to be 0 as well, because the value of capital F can't change as the value of x changes. The value of capital F has to be locked in as 0. Okay, so then that means this side of the equation is 0. That's a 1. And I can rewrite this a little bit. I can rewrite this as 0 equals the partial of f with respect to x. And the partial derivative is allowed to be non-zero, just not the total derivative. Plus the partial of f with respect to y, dy dx, plus the partial of f with respect to z, dz dx. Okay. Our goal is to eventually find the partial of z with respect to x, and so as a first step, we're going to go ahead and rearrange to solve for the total differential, the total derivative of z with respect to x. And if I rearrange to find the derivative of z with respect to x, then this is going to be minus the partial of f with respect to x, minus the partial of f with respect to y dy dx, all divided by the partial of f with respect to z. And let me take a little aside moment really quick. We'll pause right here, and I just want to remind you of something quick. The total derivative of, let's say, lowercase f, and let's say that f is a function of just x and y. The total derivative is going to be the partial of f with respect to x dx plus the partial of f with respect to y dy. Okay? So if I want to take the derivative of lowercase f with respect to x, this would be the partial of f with respect to x times dx over dx plus the partial of f with respect to y dy dx. Dx over dx is just 1, so I can forget about that part. And what I want to point out here is that this is the ordinary derivative, right, of f with respect to x. And this is the partial derivative of f with respect to x. And so the difference between the ordinary and the ordinary derivative and the partial derivative is that the ordinary derivative includes the partial derivative and also includes the effects you get from other variables that are just indirectly exerting some influence whenever you change x, okay? That's the difference between a partial derivative and an ordinary total derivative. Now that you remember that, I want to look back here and say, this is the total derivative of z with respect to x. So there's going to be part of this that's the partial derivative of z with respect to x. And then there's going to be another part that accounts for, indirect influence that we get when we change x from other variables like y, for example. So to sum up here and get to the answer, the partial of z with respect to x is just going to be the part with negative partial of f partial of x over partial of f partial of z. The difference between this total derivative and the partial derivative is that the total derivative includes the partial derivative here and also includes some effects that happen indirectly because we've got this middleman y, and y is also a function of x. So if you change x, then it's going to result in some change in y, and it's going to result in some change in capital F. But if I'm only asking about the partial derivative, I get to ignore the sort of indirect influence that we get there. Does that make sense? Okay. All right, now let's do some examples with this. So it says, find the partial of z with respect to x and the partial of z with respect to y for the following relation. This is already given to us as a function of x, y, and z equal to 0. So if I want to find the partial of z with respect to x, I can use that formula that we just derived. That is, we can use negative partial of f with respect to x divided by partial of f with respect to z. Okay. Again, this whole chunk is capital F. So the partial of f with respect to x is not super easy to find because you have to think about things like product rule and chain rule whenever we do this. But the first term is 3x squared z, and so partial with respect to x is going to give me 6xz, but then plus, no, never mind. Sorry, we're just taking a partial derivative. Okay. The second term is going to be minus 2xy squared. The next term is going to be 6x squared. The next term is going to be a 0, yeah, and then the 0, and so we're actually done. This is nicer than taking total derivatives because you don't have to worry about the little, chain rules and everything. You're only worried about partial derivatives. That makes it a little faster. Okay. Taking the partial with respect to z then is going to give me 3x squared, 0, 0, plus 3y. There we go. All right. I don't see any way to simplify that, so I'm not going to try. And so, likewise, if you wanted to take the partial of z with respect to y, all you'd have to do is say minus partial of f with respect to y. Yeah, we're just replacing the x's with y's. Okay? And then divided by, yes, partial of f with respect to z. Okay. What if I wanted to take the partial of y with respect to x? What would that formula be? Yes, you're right the second time. The negative partial of f with respect to x over, yeah, there you go. And then if you wanted to take the partial of x with respect to y, you would just swap the positions of the x's and the y's. Yeah. Okay. Or if you want to take partial of x with respect to z, you just look at the partial of z with respect to x, and then you would swap the positions of the x's and the z's. Yeah. Okay. Skip down to this one. Find partial z with respect to x here. So again, the numerator is minus partial f with respect to, yeah, over partial, yeah. Cool. All right, what goes in the numerator? Minus z minus y. Or you could do this, right? Okay. And then in the denominator we would have x plus y. Cool. All right, let's switch it up a little bit and let's find the partial of y with respect to x. So this would be the partial of f with respect to x, f with respect to y. Okay. Yeah. And then in the denominator?
Cosine y plus z times z. No. So you just times one.
Yeah. Cool. So 1 over cosine is also called
Z
secant. So it's like negative secant y plus c, but that's not necessary. Okay, let's do partial of y with respect to z here. So that formula would be negative. Yeah. Okay. This isn't quite in the right form. I have to have something equal to 0, but that's easy to rewrite. I can just write z minus e to the x sine y plus z equals 0. Okay, so now my f is all of this stuff. Okay, so it goes up top. Yeah, the e to the x is just going to act like a constant, and then cosine y plus z. Okay, and what goes in the denominator? Okay, you could actually simplify that a little bit. Because this is like that, and that's negative 1 plus e to the negative x secant y plus x or something like that. No, y plus z. Yeah. I think that's right, but could be wrong. You get the idea. Okay. Let's find partial x partial z this time. So that formula would be minus. Oh yeah, z. And then partial f. Partial x. Y squared plus 2z. And then that's it. Yeah, and notice this isn't quite in the form f of xyz equals 0, but it's fine if the right-hand side is just a constant, because when you take any of the partial derivatives, the constant goes to 0 anyways, and so really the constants are completely inconsequential to this whole thing.